welcome to This Explainer. I'm so thrilled you're here today because we're going to take some concepts that usually live trapped inside dense, heavy textbooks, and we're going to see exactly how they are operating all around us, right this very second. We're diving into the often misunderstood world of thermal physics. But, we aren't just going to be memorizing formulas today. Instead, we're going to figure out how these complex, invisible scientific topics function daily in your actual life.
Okay, let's just dive right into it by asking kind of a wild question. Why exactly does your hallway thermostat click when the room gets chilly? And on a much, much larger scale, why are global ocean levels rising? Now, you might think a small, everyday home appliance and massive global climate shifts have absolutely nothing in common, right? Well, the hidden laws of physics governing both of these phenomena are actually exactly the same.
To solve this everyday mystery, we really need to clear up a massive misconception first. We have to separate two words that we all constantly use interchangeably: heat and temperature. The true scientific distinction here is actually super fascinating. Heat is the actual process of energy transfer. It's the active movement of energy between objects because of a difference in their temperatures. On the flip side, temperature isn't the energy itself. It's simply a property that determines whether or not objects are in balance. Physicists call this a state of thermal equilibrium. So the absolutely crucial point to remember is that in your daily life, heat really only has one setting. It always, always flows from the hotter object to the colder one. Just picture holding a hot cup of coffee on a crisp winter morning. The heat is actively transferring from that ceramic mug directly into your hands, not the other way around. And this exchange of energy, it continues relentlessly, molecule bumping into molecule until both objects reach the exact same temperature. That is thermal equilibrium, where no more net energy is exchanged between the two. This perfect balance is governed by the extremely intimidating-sounding zeroth law of thermodynamics. I know, it sounds like some highly classified rule from a sci-fi movie, but don't let the name scare you off. It really just states that if two distinct objects, let's just call them A and B, are separately in thermal equilibrium with a third object, C, then A and B are in perfect balance with each other. It's basically the core logical rule that allows us to define what temperature even is in the first place. And here is the real revelation. That mysterious object C isn't some abstract theoretical concept at all. It's literally just your everyday thermometer taking a reading. When a thermometer or object C balances its temperature with object A, it gives us a reading. If we move that exact same thermometer to object B and get the exact same reading, we know for an absolute scientific fact that A and B would not exchange any heat if we touched them together. They are sitting at the exact same temperature. But, how does that little device actually know the temperature? Well, thermometers give us a reliable reading by measuring physical changes in everyday materials. They don't magically measure temperature directly. Instead, they measure physical properties that reliably change as things get hotter or colder. We're talking about things like the volume of a liquid expanding in a tiny glass tube, the length of a solid stretching out, or even how the electric resistance wildly fluctuates inside a conductor. This highly reliable physical change is the whole foundation for the temperature scales we check every day on our weather apps and kitchen ovens. When you look at how these scales compare, the Celsius scale, which most of the world uses, is neatly based around water. 0 degrees is freezing, 100 degrees is boiling. Fahrenheit, super common here in the US, puts those points at 32 and 212 degrees. But the Kelvin scale, now that is the truly fascinating one for scientists. What's just completely mind-blowing is that the Kelvin scale starts at absolute zero, a freezing negative 273.15 degrees Celsius. And unlike the others, Kelvin doesn't even use the degree symbol. You literally just say Kelvin. At this theoretical point of absolute zero, gas pressure would effectively drop to nothing. But what's truly amazing about this number is that it represents a temperature that has actually never been reached anywhere in the entire universe. No way, right? Because scientists need extreme, unyielding precision instead of just measuring boiling or freezing points, which, can notoriously fluctuate with things like air pressure. The modern Kelvin scale is defined by two absolute constants. The first is that theoretical absolute zero we just talked about. The second is the specific triple point of water. This is an incredibly specific condition, occurring at exactly 0.01 degrees Celsius and a specific pressure, where water exists as a solid, liquid, and gas all at a perfectly stable equilibrium. It's a completely unchangeable constant, giving scientists a flawless anchor for their measurements. But let's get back to how our daily world actually functions, which lies in a very simple fact. Most substances expand when heated. At ordinary, everyday temperatures, the microscopic molecules that make up solid objects are just vibrating with a small, quiet amplitude.
But as you pump heat into them and the temperature spikes, those molecules get incredibly energetic. They start vibrating with much larger amplitudes, actively pushing further and further apart. Because of this frantic microscopic dance, the object as a whole literally has to expand in physical size.
And you can clearly see how that thermal expansion happens in 3 different ways depending on the physical shape of the object. If you heat up a long rod, you'll mainly notice linear expansion, stretching it out in one dimension. If you have a flat sheet of material, it expands in 2 dimensions, which we call area expansion. And for a 3D object, like a heavy block of metal, it expands outward in all directions, and that's known as volume expansion. Let's totally ground this in a real everyday scenario. For example, when you're heating up a 350-degree oven to bake holiday cookies, the physics of thermal expansion are hard at work right inside your kitchen. That rectangular steel baking tray you slide into the oven, it undergoes area expansion. Because the temperature change is so drastic, going from room temperature to a scorching hot oven, the metal's molecules vibrate wildly, and the tray literally grows in measurable surface area while it bakes your cookies. We can even harness this unavoidable thermal expansion to control our home's climate. Remember that thermostat we talked about at the very beginning? Well, it works in 3 simple steps using a clever little component called a bimetallic strip. First, the room temperature drops. Second, 2 different metals fused perfectly together inside the strip react to that drop. And third, because they react differently, the strip physically bends to interact with an electrical circuit. To understand why that bend happens, just imagine a strip made of 2 different metals, say brass and steel, glued super tightly together. Brass has a higher coefficient of linear expansion than steel, which is just a really fancy way of saying it reacts much more extremely to temperature changes. When the room gets cold, the brass shrinks much faster than the steel. Because they are permanently fused together, that unequal shrinking forces the entire strip to physically curl and bend downwards, closing the electrical contact and turning on your heater with that satisfying click. And zooming out to your broader daily life, this exact same science explains so much more. Take Pyrex glass, used in measuring cups. It is specifically engineered with a low coefficient of expansion so it doesn't experience massive thermal stress and shatter when you pour boiling water into it. And on a planetary scale, this explains our second mystery. As global temperatures rise, the water molecules in our oceans vibrate with larger amplitudes. The oceans literally undergo volume expansion. So even without melting ice caps, warming oceans simply take up more physical space. We are talking about trillions of gallons of water undergoing volume expansion, causing rising sea levels globally. So we've gone from the microscopic vibrations of individual molecules to the clicking of your home thermostat, all the way up to the expanding, massive volume of our planet's oceans. It's just wild that everything is connected by the simple, beautiful rules of thermal physics. Thank you so much for joining me on this explainer. The next time you adjust the thermostat, you know the microscopic dance you're controlling. But it really begs the question, what other hidden laws of the universe are dictating the everyday objects you completely take for granted? Stay curious, and we'll see you next time.